Hello everyone, we're Group 23. The name of our project is Saber Smart Breaker. My name is Eliezer Urdaneta. I'm an electrical engineer for this project.
Hello, I'm Carter. I'm a computer engineering major.
My name is Emmanuel Lopez, and I'm in electrical engineering.
Hello, my name is David Rosine, and I'm majoring in computer engineering.
Motivation and background. At the last stage of the distribution process for electricity, we have the electrical circuit breaker, a device made to protect the circuit and the branch where it is installed. Our objective is to make this device better, making it smarter. As we know, uh, circuit breakers protect your system against multiple fault conditions, overheat, overload conditions. Our team was tasked by Dr. QC from the University of Central Florida and her company, Greek Interactive Teams, also the sponsor of this video, to innovate the design of this conventional breaker to keep up with modern standards. While conventional breakers have been reliable for decades, their design comes with important limitations. The first one, they lack real-time monitoring and data logging capabilities. This means homeowners and facility managers have no visibility into how power is being consumed, no way to analyze usage patterns, and no early warnings of abnormal conditions. The second one, and from my opinion, the more important one, is that traditional breakers do not offer remote management. If a fault occurs while the building is empty, there is no way to assess the situation or respond without being physically present. And this is the first limitation we need to change if we want to implement smart grid ideas into the electrical grid. Third, their diagnostic capabilities are extremely limited. Conventional breakers cannot monitor their own health or provide predictive maintenance insights. Over time, mechanical wear contacts degradation or repeated fault interruptions may reduce reliability. Goals and objectives. Within our basic goals, we are aiming to build a smart circuit breaker capable of protecting against overcurrents, short circuits, and ground faults, while still meeting the major electrical safety standards, even in our reduced and safe prototype scale. Second, we're aiming to integrate a built-in communication system. The idea is to allow the user to access through a web interface so users can see what's happening in real time, control the breaker remotely, and access predictive maintenance information, all through a simple and user-friendly platform. Third, we're looking to provide predictive fault detection analysis to inform the user of irregularities during the power consumption and tell him like, hey, it's time to look for a replacement, right? And four, and then one of the more important ones is to minimize the power consumption because we want to make this a feasible economic solution, right? Now with our advanced goals, we want to integrate sensors able to send data through communication so we can monitor in like lifetime on the website. Um, Incorporate components capable of standing surges to prevent replacement and repair at later times. This meaning we're not going to use fuses because it's not a feasible solution here. Implement temperature monitoring to warn users of potential heat surges or five within the system, and create a user-friendly, easy-to-install system where one can easily uh, do any change you need to on or turn off any branch that you need. Overall system specifications, we have a voltage and a current capacity. We want to keep given the project constraints by our advisor. We have a minimum trip time response and interrupt rating for this project, scale it to, or power capacity overall, or the power consumption of our electronics power will be 10 watts or less. Or operating temperature will be between, -10 Celsius to 60 Celsius. And the approximation to our dimensions will be 120, 25, 70 millimeters.
So now we will be working on our hardware block diagram. So starting our hardware block diagram, we have our 24 volt 5 amp AC input, which is directly fed into two sections of the PCB, those being the regulator PCB and the sensor PCB. The regulator PCB changes the AC signal into a DC signal using a full wave rectifier, which is 4 diodes followed by a capacitor. And then it uses a switch-in regulator to achieve the desired voltage for the following peripherals in the sensor PCB. The actual AC load line will then continue through passing directly through the solid-state relay and the Hall effect sensor, so that the current can be monitored directly like that. And then the temperature sensor will be used to maximize measuring heat directly from the AC signal trace. The MCU takes in data from the two sensors, and depending on the read values compared to what is set in the software, will toggle the solid-state relay directly, allowing current to flow in or out of the sensor PCB and into the load. All at the same time, the MCU is driving the values of the measurements to an LCD display for local monitoring, and sends the data read to the server to be able to be viewed remotely. The rest is being transmitted to a website for remote reading and toggling. There's also a manual physical toggle switch, and as I said before, the LCD, you can see all the values and all readings from the breaker itself if needed. For our hardware selection, primary gate component selection, we had 3 main choices that we were looking at, and a couple of specifications that we were really focusing on. So the first component, or the first specification that we wanted to look at, was the average switching speed. Well, the NFPA and IEEE don't have a specified switching speed for conventional breakers that are used nowadays. We decided on 10 milliseconds should be the absolute slowest, since that is typically how fast a normal breaker works. Seeing here, we see that the solid-state relay had the fastest. As for isolation, that really correlates with our durability, which is the second specification that we really wanted to look at. Though the mechanical relay says it's high, the solid-state relay does, in my opinion, offer a better alternative, because it uses a MOSFET Zener diode configuration with a dedicated onboard optocoupler to drive the internal FETs and appropriately toggle the circuit accordingly. So we chose the solid-state relay for that. It also had low current in the microamp range. It was also very small, though it is a bit more expensive than the other two configurations. It's definitely worth it for its size and its isolation, and therefore its durability. It should be able to last for a much more longer period than conventional breakers and these other two configurations. For choosing our current sensing methodology, there were 2 real methodologies to go about doing this. The first being a current transformer with a shunt resistor. It requires a magnetic coupling between a primary and secondary winding, which produces a lower current passing through directly. A known shunt resistor to get an analog voltage proportional to the current going across. However, it requires its own mid-supply biasing and shunt resistor tuning, Without proper precautions, it can lead to supplying an unsafe voltage to an MCU analog to digital converter. For the Hall effect sensor, it provides its own analog voltage proportional to the current going across. It's already biased with the midpoint of half the sensor's supply voltage. Additionally, it's very compact compared to the current transformer and has a cheaper cost. The way the Hall effect current sensor works is that current will pass through a short, and through this short, a magnetic field is produced, which pushes charge carriers from one side of the semiconductor material to the other, which in turn produces a voltage known as the Hall voltage, as seen in the equation below. This Hall voltage will then be transferred over to our MCU, where we can read it directly, as the voltage will be proportional to the amount of current produced. Over on our right, you can see the specifications. For our purposes, the specifications have been limited drastically, though we can alter it to be maximized, though it will be more costly. Comparing voltage step-down methodologies, we have the AC transformer, the linear regulator, and the buck regulator. So strictly using an AC transformer would in conjunction with a full bridge rectifier would be best in terms of efficiency. However, finding one to match our needs while also maintaining a small form factor to fit in our chases is a little impractical. Using a linear regulator to drop down from peak amplitude of 36 volts DC down to 5 volts DC is inefficient due to the heat generation produced, which could affect our temperature sensor readings and could possibly harm the components. This leads to us using switching buck regulators, which are slightly less efficient but more space efficient, and as for the rest of these factors, they outweigh everything else. Here's our table of buck regulators that we looked into. Initially, we selected the LM5180 due to it meeting all the required criteria, while also allowing it to be used in conjunction with a switch mode power supply transformer to provide the feedback regulation to the integrated circuit itself, and also providing isolation between the primary and secondary sides. However, this regulator proved to be a pain to manage, increasing loads even those within what is supposed to be considered in the safe range, would lead to burnouts or voltage drops, or could cause the regulation to overshoot the maximum range and burn the regulator entirely. Dr. Weeks recommended that we use the LM2576HV, a much more consistent regulator with a simpler topology, providing more headroom in terms of current that can be drawn from it. Seeing its specifications, there's not much differences that can be spoken about. The efficiency is rather average between the two. The size, though it is the biggest, it still is relatively small when seen in our PCB, and its max input and max supply current show that it definitely meets our needs.
Alright, so here's kind of a software flowchart for the embedded portion on the microcontroller itself. So we'll cover the startup sequence first. Upon startup, it's going to prompt the user whether or not they want to use the onboard credential saved in non-volatile storage, or if they'd like to input new ones. If, for whatever reason, they want to put in new ones, it will go through the process of prompting for Wi-Fi credentials, establishing connection to the WebSocket server, and then prompting to connect to an account that's already registered within the database. If they already have credentials saved, then after 5 seconds, it will default to just using these, and then it will go to the actual measurement portion. So once the sequence passed, it's going to immediately toggle the solid state relay to allow current to flow, and at the same time, it's going to start measuring data and displaying it on the LCD, and also transmitting it to the web app interface. If at any time the load or the temperature exceeds the defined max, it's going to toggle the SSR to block the current flow. At the same time, there's a local manual toggle, and as well you can do a remote toggle from the web app interface, and obviously depending on if the device is active or not, it will either toggle to block the current or toggle to allow current to pass. So measuring a DC signal with the Hall effect sensor is pretty trivial, assuming that your current isn't changing at all. It's just going to produce a analog voltage proportional to that current that's going across it. But with an AC signal, however, there are some other things to take into account. So obviously, since the AC signal is alternating, depending on where a sample is taken, an individual sample is taken along the waveform, you're going to get a different proportional voltage corresponding to the current going across it at that exact moment. So if you just kind of looked at the waveform to the left, like if you took an individual sample at the far left side, that would be different from if you took the individual sample in the middle or the right side. So to properly account for this, we take n number of samples along a given time window that corresponds to a number of full waveform cycles. In our case specifically, we're only measuring one cycle per like actual measurement produced. So to actually capture meaningful data from the changing waveform, we sample with according to Nyquist's rule, which just states that the sampling frequency has to be at least twice that of the incoming signal. In our case, this is a 60 hertz signal, so we need at least 120 hertz sampling frequency, but this is super trivial for a microcontroller to do. So we found that between like 1 and 5K kilohertz is a sufficient sampling frequency to capture meaningful data while also not completely bogging down computation. So once all the samples are taken, or I should say as each sample is taken, they're individually squared and summed together, and then we square root the mean of the samples to get the RMS voltage, and with that we can find the RMS current by using the specific conversion specified by the sensor within the datasheet.
For the microcontroller, we compared 5 candidates. The ESP32 stood out because it has a dual-core 240 MHz processor, which is the most powerful on the list. It also has 520 kilobytes of SRAM. It has a built-in Wi-Fi, which is essential for our web communication, a 12-bit ADC for precise sensor readings, and it operates at 3.3 volts. Most importantly, the development board costs only $8 and the individual modules are $7, making it by far one of the most cost-effective options out of all.
Okay, so here's the first PCB board, and it essentially acts as the hub for all the other PCBs and their associated power deliveries, sensor, and peripherals to interact with the microcontroller itself. So obviously we have the ESP32 located on here, and it's powered through the 5-volt header pin, which connects to a 3.3 LDO regulator to deliver proper voltage signals to power the ESP32 itself safely. We have a USB-A header pin, which connects directly to the CP21 and 2 USB to UART bridge controller for programming and serial communication. We have a dedicated programming pin header, which will connect to the buttons on the outside of the chassis for ease of access to putting the controller into proper boot mode for actually programming it. In addition, we have a dedicated 5-pin header for all the associated sensors located on one of the PCBs. And finally, we have a dedicated 9-pin header for the LCD driver board to properly interface with the ESP over SPI.
Here is our regulator PCB. Our untouched input signal goes directly into a full wave rectifier, which is 4 diodes capable of maintaining the 24 volt 5 amp supply, fed into a 4700 microfarad capacitor, which is that large due to the high voltage and current needs. It's then fed into a step down regulator, the LM2576H as said before, and then finally into the output where it can be fed into the sensor, LCD, and MCU PCBs. As seen in our PCB diagram above, the traces are noticeably larger to compensate for the large input signal.
Okay, and here are just some images from our prototyping phases. So starting top left going clockwise, we have the transformer here to set up our test conditions, outputs 25 VAC with a max of 5 amps. The next photo that can be seen is an initial prototype of our buck regulator, and you can't see off screen, but it was being powered from the 25 volt AC signal itself through a full bridge rectifier, and as you can see, it was outputting 4.7 volts. This is just because this was an adjustable version with feedback resistors, and I didn't have the necessary feedback resistors to get exactly 5 volts, but the general premise held. Next up, this was just an old photo of one of our initial configurations with the original regulator we had used, and just showcasing a lot of the different components that we had in here. So that bottom piece is the solid state relay, and then this final photo here was I had my multimeter connected in series with the load, and we were measuring 1.3 amps from the multimeter itself, and then to the left of that is a serial monitor output, just showcasing the measurements that were taken on board the ESP itself. Okay, and just some more photos from prototyping and testing. So on the left side here, you can see our kind of pseudo terminal interface. So during the startup sequence, as you can see, it says it's going to default to existing credentials and then connected to the Wi-Fi and then the server. On the right side there, you can see kind of just a breadboard layout of everything that we had going on. And at the time, we had about 1 amp passing through, and I think we had the defined max set to 1.2 amps. Is that what it says? And then on the bottom, just a showcase of the real-time monitoring between the LCD screen itself and then the web application in the background. Okay, and here's just some data that we captured during our testing phases. So at the top here, this was the average error for a given sample selection compared to the known current. So we had a high wattage potentiometer that we could use as a method of easily varying the load connected. And for each value that you see on the x-axis, we took roughly 20 samples each. And based on this preliminary assessment, we found that the average deviation from the target current to be about 50 milliamps. And I would suspect that this would be a little bit lower because the measurements taken at 1.82 seem to have a noticeable outlier compared to the rest of the sample selections. In addition, we were able to calculate the worst case and roughly the average time from window sampling to when the SSR actually toggles off. And based on the current configuration of taking 100 samples at a 6 kilohertz sampling frequency along a single waveform cycle, we were able to determine that the average or the worst case was roughly 17.7 milliseconds and averaged around 8.2 milliseconds. Currently, this matches exactly what conventional circuit breakers see when a short occurs, but we are looking to implement a different algorithm that takes a running total of the RMS samples at each individual time point along the cycle to have a current running total, and if that current total ever exceeds the specified max, then it will flip instantly and be the time will be much more dominated by the SSR itself, which would be closer to 1 millisecond. In this current implementation, the time for the toggle time is highly dominated by the actual sampling window itself. Okay, and here's a showcase of comparisons between different languages and development frameworks for the embedded programming section. So starting off with the programming language comparison, there were really 3 options to choose from: C/C++, MicroPython, and Rust. And overall, we decided to go with C/C++ due to its library ecosystem, speed, and relative ease of use. It's not as easy, obviously, to use as something like MicroPython, but MicroPython suffers from the fact that it's mostly an interpreted language, which makes runtime much slower as compared to C. And or Rust. Rust was an option, but due to the fact that it had a much steeper learning curve, it was kind of a turnoff for us to use. And in addition, the library slash documentation support is nowhere near as vast as the other 2 options.
Here is our sensor PCB. It starts out with our untouched signal going into our Hall effect sensor, which produces the Hall voltage as discussed earlier. It's just going to be input into the pin HD-1X5 header pin. This feeds into our MCU board, which feeds into the MCU, which will consider the code and then output a signal to our solid state relay, which tells it to either open the signal or close the circuit to allow current to flow through into the load. The temperature sensor is being fed into our MCU board, being input from our regulator PCB for voltage or for power supply. The temperature sensor will monitor the heat over the entire board to make sure no overheat occurs.
Okay, here's the fourth and final PCB board, and this acts as our driver board for the LCD display. So on the far left side, we have a 9-pin header with the associated SPI communication lines and a power pin for directly, obviously, powering the display itself. The display runs off a 3.3 volt signal, so we have a linear regulator on board to drop the 5 volts down to a 3.3 volts. In addition, this 3.3 volt signal will go through a constant current driver to constantly output 60 milliamps to the backlight itself. And the LCD itself has a embedded TFT driver, so which is connected to a 30-pin ribbon cable, which will connect to the 30-pin connector that can be seen on the right side. And in this format, it can be interfaced through the SPI communication protocol.
Here is a look at the full stack comparison for the web app. For the front end, we chose React over Angular. The reason for this is because its virtual DOM effectively handles high-frequency UI updates. In a dashboard where the sensor data changes every second, React ensures that the interface stays fluid without constant re-renders. For the back end, we chose Node over Python. The reason for this is because of its non-blocking event loop. It's purpose-built for high concurrency demands of IoT, where a single server might need to maintain thousands of open socket connections simultaneously. For the database, we chose MongoDB because it offers flexibility that we need for the varying sensor payloads, and it's optimized for high volume write operations required for continuous data logging. And for the communication protocol with the MCU, we chose WebSockets over HTTP polling. The reason for this is because WebSockets reduce the overhead by keeping one connection open, whereas HTTP requires a new handshake for every sensor update. Here is a further look at the programming language and our stack. On the front end, we used React with TypeScript. This provides type safety, component reusability, and a responsive UI for our dashboard, our setting, and our authentication pages. On the back end, we use C++ via the Arduino framework on the ESP32. This handles real-time sensor polling, fault detection logic, SSR control, and Wi-Fi communication. For the back end, we use Node and Express. This is a middleware layer that exposes the RESTful endpoints for the ESP32 so we can post sensor data and provide a WebSocket server for pushing real-time updates to the React dashboard. For the database, we used MongoDB. This is used to store persistent sensor logs, device configurations, and user profiles. For the communication protocols, we used REST APIs. They were used for standard CRUD operations and interactions with the database, like logging in, authenticating, and others. And for the WebSockets, the MCU posts sensor data like temperature and the current to individual WebSocket connections based on the matching device ID and user ID. It allows for full duplex communication with minimal overhead relative to the standard REST API. Here is an image of the use case diagram for our web application. Here there are two actors, a new user and an existing user. A new user can register, which always includes providing credentials through an include relationship, and that gets authenticated and stored in the database. An existing user, on the other hand, they can log in and access the dashboard, which gives them three core abilities. One, monitoring their breaker status. Two, remotely controlling the power so they can remotely turn off the breaker or turn it back on. And three, receiving fault notifications. All three of these actions go through the authentication action before reading or writing to the database. And then the user can also access the setting or contact page and an about us page after they log in. Here we're going to take a look at the register and login page for the website. So on this screen, it shows the register page. Here, the user is able to input their first name, their last name, their email, and they're able to set a password. So we're going to take a look at an example. So in this case, the user put in the first name, they put in their last name, but they put in an invalid email because it doesn't have like the add and then like the whatever. So it shows here invalid email. And then under the password, it shows that the password should include at least 6 characters. So they won't be able to register without meeting those specifications. And here on the login page, a registered user can put in their email and their password, and they'll be able to access the main web app. Here is a look at the main web app. So on the sidebar, you can see the 4 main pages you can access: the dashboard page, the settings page, the contact page, and an about us page. So on the dashboard page, here you can see all the connected devices you have, and then you can disable them. You can also see data, their sensor data like temperature and the current going through, and you're able to add new data, and you're able to add new devices or delete some devices. On the settings page, there you're able to access your user settings and change some of your user informations, and you can also access some of your devices from there. The contact page is just a way to reach out to us, the developers, and then about us page, it just lets you know more about the smart breaker, what it's about, and how to set it up. Also, at the bottom left, there are 2 things: the change account. So if a user has multiple accounts, they're able to switch between their different accounts here. And then we have a logout page that lets you log out of your current account.
So here's just a table showcasing progress and status for different parts of our design. So prototyping and testing has been complete. As of now, our first iterations of PCBs have been fabricated, ordered, and assembled. The testing of our PCBs has been mostly completed. We've tested 3 of them, with the exception of the main ESP board, due to the fact that the CP2102 onboard regulator is not properly regulating. It's like requiring an additional 3.3 volt signal to actually read as a USB device. So that is something that we need to parse out. Chassis design and fabrication is currently in progress. And then the website design is in progress. Most of the main features are mostly completed, but just additional styling is needed to make it fully fledged. And software design, specifically the embedded software design, is mostly completed. Once again, it just needs some more styling and potentially some small changes going forward. Okay, here's a timeline of the future plans going forward. So by the end of this week, we'd like to have our initial testing completed. We already have our current PCBs soldered and assembled. For if any reason over this, by the end of the week, if we find any discrepancies or problems with our current PCBs, we're going to make revisions and order new ones. Assuming that's the case, we expect the new PCBs to arrive around the beginning of March. And then hopefully by mid to late March, we'll have those soldered, retested, and integrated with the rest of the system. At the same time, we're going to be doing the 3D modeling and assembly of the chassis itself. And in addition to that, by the end of March, we'd like to have the web interface fully polished and complete with all of the necessary features. And by the beginning of April, we'll have all of our final revisions and anything else that needs to be sorted complete by the 7th of April.
This is the end. Thank you for your attention.